of Pierre Cartier, the mathematician. As many of you well know, he was an associate of the Bourbaki group for over 30 years. He estimates that he wrote 200 pages per year for Bourbaki over that time.
That you will not never see.
But you'll never know exactly which ones are his.
Yeah.
It's really impossible to pin down his interest in mathematics, as his interests are so broad. He's worked on algebraic geometry and algebraic groups, representation theory, mathematical physics, category theory, probability. Many mathematical objects and constructions are named after him. He's known for the Cartier operator in algebraic geometry and characteristic P, duality of abelian varieties. He's also, the Cartier divisor is named after him. It's been a great pleasure collaborating with Pierre and having him with us over the last couple of weeks. This afternoon he's going to tell us about his cosmic Galois group, a tale of geometry, number theory and physics. There is a dinner planned. At the end I'll just ask for a show of hands. Thank you.
So I may need an apology for the title Cosmic Galois. But I was led by analogy with my colleague at IHS. Ruel, that you know, speak of strange attractors. And Icon speaks of non-commutative geometry. Tom spoke of catastrophes. Okay, this is just so mysterious that I wanted to add some mystery. And I invented 15 years ago the catchword Cosmic Galois. Now I have to explain to you what it means. It started when in 1998 we had the 40th anniversary of our institute, and I was asked, there was a special volume published at this occasion, I was asked to write a paper about symmetry. And my paper was written as the notion of space from Grothendieck to Kontsevich and Kohn. So it was the notion of space, as you know, is very deep, and it's philosophers and mathematicians and physicists have spoken at length about that. My favorite book is the one by Hermann Weyl, Space, Time, Matter, which is a very, very deep book. Very deep book about the finding of Einstein and what came after. And so then at the end, I dare to make a conjecture to, well, it's not a conjecture, fortunately, you will see why. It's a project or a program. It's not a conjecture because, as you will see, at the time we had some information and many people believe in some facts, mathematical facts, which were not, which were contradicted soon after. But the contradiction was not so easy, Well, not so, it took 10 years to find contradiction with him. That means that I had spoken of a certain class of numbers and the class was larger than we expected. But I think since I did not commit myself to any precise statement, I said it's a program and we should look in this direction. The main idea survived, Of course the technique had to be revised, but the main idea survived, and I will explain it. The idea is to make a merger of two completely different ideas. The standard model in quantum field theory, quantum physics, I will just describe it quickly, and one of the most surprising discoveries of, prophecies of Grothendieck about the so-called motives and motivic Galois groups. So the deepest idea in the algebraic geometry should have to come in connection with quantum physics was not expected, of course. And at the time there was some analogy, and it was led by some analogy, and I want to present to you this analogy. Okay, so, and I also to say that the most recent part has been done in collaboration and under the influence of Francis Baum, who was my PhD, defended his thesis in 2006, is now a permanent member in my institute. So I had a very good PhD, but I think not at that level. Okay, so, okay, let's begin. The standard model. Which is a model, which is a mathematical construction, which is supposed to represent all the events that we have observed in high energy physics. The big accelerators are the one in Geneva, LHC, the Fermilab, this country, etc. So an enormous amount of experimental data have been observed, but they have been organized, and but the organization is a kind of monster. Alain Kohn is prone to show to show the full Lagrangian of the theory, which take two printed pages with a lot of indices, sign, etc. And I will explain what it is behind it. And the point is that we want to put this system is very complicated. It has been confirmed by all experiments so far, and the latest discovery in 2012 of the so-called Higgs boson confirmed all the predictions.
Excuse me, allegedly confirmed.
No. I heard a recent report by experts, and no, now it's completely settled. Now it's settled. They know the mass of the new particle up to 1%. And
they believe it, no?
Okay, right. Okay. No, I think it's no reason to discuss it at the moment. Okay, so the standard model is based on the idea that there are various kind of particles. There are the so-called leptons, or no, I'm sorry, fermions, whose spin is 1/2. There are the bosons, whose spin is, well, gauge boson, whose spin is 1. And there is a Higgs boson, whose spin is 0, which is a new feature, it has never been observed before, and, quotation mark, a graviton, a particle which was responsible for the gravitation, whose spin is 2. This
but
is
that would not be part of the standard model.
No. Exactly. No one is able to make the connection between properly gravitation and the standard model. That's a big challenge. So I will not speak about that, but of course in elementary terms it represents a graviton particle which could fit with this, but it's not part. For the moment it's not part. Okay, so now...
Muscle.
Now here is a list of the particles. For the fermions you have 12 particles. You have 6 quarks, which are called U, D, C, S, T, B. 6 letters to represent the six quarks, which have the unexpected property that the electric charge is -1/3 and 2/3 in terms of the basic charge, electrical charge, which is a charge of the electron or the proton. So it was very unexpected that there should be fractional charges. So now it's well understood, and at least it's well understood, but it would make a model for nuclear physics. At the moment, it's very strange. Nuclear technology is extremely developed and supposedly safe, but I don't think the technology itself has to be blamed. So it's known that a proton should be UUD, composed, and it fits with the electric charge, and so this is a proton. This is the neutron should be UDD, and the charges have been, the charge is +1 and the charge is 0, that the charge have been adjusted. But so it means that in the nucleus of uranium, there are not 238 particles, proton and neutron, 92 proton and 146 neutron, but there are 3 times more, 714 quarks. And that's so. At the moment, it's such an enormous amount of particles, such a large number of particles, that no one has been unable to model starting from scratch. We have ad hoc model, phenomenological description, which are enough to deal with nuclear technology, but basically you can say nuclear physics is totally ununderstood. Well, it's a slight exaggeration. So that's what the ordinary matter. The ordinary matter is built out of neutron and proton. That's the cheapest description. More precisely, out of this quark. Of these quarks in ordinary matter, only U and D appear. The other one are exotic. Okay, now there is another sequence, which is the electron and its cousin, mu and tau. The electron, which has a negative charge, they are all negative charge 1/2. All these have spin 1/2. And to each of these lepton corresponding neutrino. All these are very well established. So you can say that matter is built out of these 12 particles. Well, these are exotic. These are exotic. So really you have proton, neutron, electron, and neutrino. Electronic neutrinos. Okay, now what comes next is spin gauge boson, and they are responsible for the interaction. First of all, the first interaction is between electron, but electromagnetic interaction, and it's given by the photon, whose standard symbol is gamma. Photon invented by Einstein in 1905, and since that's very well understood. And the photon is what mediates electric forces between charged particles. The mechanism is that if you have a U, for instance, it will emit a gamma, and the gamma will hit another particle, electrical particle. That's the way electromagnetic forces are mediated between particles. Okay, that's for electromagnetic. Now there are the so-called WZ. So there is Z0 and W plus or minus. This indicates the charges. And they are responsible for the so-called weak interactions. And they are arranged as a generator of a Lie algebra, which is a cell2. They correspond to a basis. I mean, Z0 corresponds to the diagonal base, the diagonal element in the cell2, and W plus and minus to the off-diagonal element. And SL2 or SU2, it's not that important. And then there is the gluons, which similarly, there are 8, so there are 3 because, and they add the group SU2 is of dimension 3. And here you have 8 because the group SU3 is of dimension 8. And they correspond to the 8, they correspond to the basic element in the Lie algebra of SU3. So, and that's, I will explain a little bit what they are called gauge boson. And it's in a similar way as a photon mediates electromagnetic forces between electrical particle, electrified particle, then these are responsible for the so-called weak interaction. And for instance, the weak interaction will couple. It will couple because, for instance, Z0 has a charge, electric charge is 0. So it will act among particles of the same charge. It will act there, it will act there, it will act there, and it will act there. But W plus and minus changes the charge. So this is W plus. So W plus and minus will represent the interaction between the two lines and also between the two lines there. Okay, that's for the gauge boson. Now the Higgs boson is a new character in this tail, and it has spin 0, spin 0 and charge 0, charge 0. And it has been introduced by Higgs and Englert. Don't forget Englert. We got the Nobel Prize with him recently. Higgs and Englert long ago introduced this in order to solve a riddle. The fact that this gauge boson, the photon has a 0 mass. the gluon have a zero mass. And in order to work perfect, to work well, as a gauge boson, it should require that these have also zero mass, far from being true. Well, I remind you that the standard unit of mass in this setup is 1 GeV, and I remind you that the proton has a mass which is approximately 0.9 GeV, so roughly speaking, the mass of a proton. And now the W, I'm not sure, but W, I think W is in the range of 80 GeV, and if I'm correct, Z0 is in the range of 70. So, very, very big, very big. The gluon have no mass. The gluon do not have a mass, gamma do not have a mass. Here the masses are much smaller, much smaller, much smaller. All these masses are much smaller, except for the top and the tau. Okay. For a long time, people thought that the neutrino did not have a mass. When they were introduced by Fermi in the 30s to solve the riddle of the time, they were supposed to have no electric charge and no mass, which makes them very difficult to detect. Finally, they were detected, but it took a long time until the 50s to be detected, and so it took even more time to discover that there were not one neutrino, but two neutrinos, and later on we discovered the third neutrino. And there are purported proofs that you cannot extend this to more than 3 generations. Or at least there is no real, the proof is not out of first principle. It says that if there was a 4th generation, some phenomena would be described as it would contradict some experimental data. So it's not a proof a priori, it's a comparison with the experimental data. So that's basically, and I say I have to add the H, E boson, and its mass is enormous because the mass is in the range of 100 GeV. And I said, they claim now they know it up to 1%. Okay, so that's a model, standard model. It's rather complicated. Even at a purely descriptive form is rather complicated. Well, you can explain that to a high school student. He can understand at least the description, not the detailed description. But what comes is much, much more difficult to describe mathematically. As in any modern theory of fields, the basic object is a Lagrangian. So, to each of these particles is associated a certain field. A field, by definition, is a 4-dimensional Minkowski space-time. So, you have, for instance, for electromagnetism, you have A, but A is a vector. It has 4 components. Or rather, what is intrinsic is a differential form, and I use the standard notation, A mu dx mu. My notation is that x0 is ct, and x1, x2, x3 are the space coordinates. Okay, so, and very often I will omit factors C and H. We all know that we can normalize the unit so that C and H is 1. And dimensional analysis tells you how to restore the proper power of C and H if you really need it. Okay, so that's it. So it's a differential form, and a differential form. Okay, now you have a Lagrangian, and there are other things. I just give you the contribution of the Lagrangian. And it's better to express this as a differential form. So it is dA exterior star dA, where star is a Hodge-Durham operator, which transforms a form of the, well, D is an exterior differential, dA is of degree 2, and star transforms a form of degree P into n minus P for the total dimension. 4 minus 2 is 2, so it's 2. So 2 plus 2, it's a 4-dimensional form. That means it's a volume form. And you can, a Lagrangian properly is not a function, it's a differential form on the Minkowski space. That, and then you want to, when you integrate it, you get the arch. That's a schema. And again, I will take H and C, this is one for simplicity. So that's it. And now we have, of course, here W and Z correspond to other fields, call them J for instance, J. And J is not J is a differential form. J is J is G mu dx mu. But G mu is not a scalar. Is not a scalar. Is an element of the Lie algebra of the gauge group. So really, this is a differential form. Differential form of first order on the manifold with value in the Lie algebra. And of course, you can consider that electromagnets correspond to one-dimensional Lie algebra, corresponding to the group U1, if you want to have a compact group, and then SU2, SU3. Well, it's very similar. You replace A mu, which is a scalar, by an element in the Lie algebra, prime over the point of the space-time. So, and you do the same, dj star dj, and that gives you the contribution, to the Lagrangian of the other field. Now, for the quark and so on, for the lepton, they are spin 1/2, which means that they correspond to a field which is a spin-off field, psi. So, a function on the space-time which has value in the spinors, and the spinors are 4 components, for 4-dimensional space. And then, well, if the dimension is n for the space, for the spinors, we think is 2 and minus 2. Okay. So psi, and then you have a well-known anti-linear transformation which transforms psi to psi bar. It's a kind of Hermitian conjugate, which is special for the spinors. And what you have is that, first of all, if you have a spinor psi, so for each of these 12 particles, you have a field psi. And for each of these particles, you have a contribution, which is the following. First of all, the mass of the corresponding particle, psi bar psi, which is, again, a differential form of degree 4, plus 1, plus a kinematical term, which is d psi, and d is a shorthand for d mu, which is a partial derivative, multiplied by the spinor operator gamma mu. And the gamma mu are the Dirac operator, which satisfies the Clifford relation, plus gamma mu is 2 times eta mu nu, well, eta mu nu because we have a Minkowski metric which is plus, minus, minus, minus. So eta is a diagonal matrix with entries plus, minus, 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 minus. Okay. So plus, minus, 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 0, 0, 1, 1, 1. Okay. So these are the Dirac, Clifford Dirac matrices or operator, and so d mu. Okay. That expresses the contribution of each individual quark or lepton, all these terms. So you have to add all these terms before each. Now, so far we don't have interaction. And well, the H is of spin 0, so I will not give anything for it, but there is a similar contribution for the Higgs boson. Now, what about interactions? The model is electromagnetic interaction. And the model of electromagnetic interaction is the following. If psi represents the electron, ordinary electron, psi bar, we want to have a term which represents the interaction between an electron and a photon. The photon is represented by A mu or A mu component. And then you write A slash, which is a linear combination of A mu gamma mu. A mu is a scalar, depending on the point of the space-time. You multiply it by the fixed operator, you get an operator acting on the psi, and psi bar is in the dual space. Psi is in some space, psi bar is in the dual space. So that's a scalar product. That's, and you put the electric charge, which is a coefficient, to tell you what is the importance of this, the strength of this interaction. Okay, so that's the model. And it can be accommodated to to the other cases, can be accommodated to the other cases. And it was a great success. That's what initially envisioned for the electromagnetism, at the cost of extending a one-dimensional group to a larger dimensional group, fits work perfectly. And all the mechanisms of differential geometry work perfectly. Okay. So now, H, I will come in a moment about H, which is special. So that you have to put all this, so we have many possible interactions, because among these, there is an interaction mediated by the electron, and a so-called weak interaction mediated by this. The gluons are responsible, the gluons also are responsible for this sector. And then, but then on this side, you have only the first two forces, the so-called electromagnetic force and weak force, act on this sector, they act on this sector, and the gluon act only on this sector. Which means that, of course, when I write U, it's really a vector with three components. If you want an action of the group, as you see, you need three components. So, we have to put all this in action. Okay, and then the H is a little mysterious, and I come now to some explanation which was given by Alain Kohn. Okay. Alain Kohn, well, if you read all the details of this, it's very, very complicated, and it has been obtained by 50 years of observation. Every time there was a new observation, you try to fit it in the model, and you put an extra term. For instance, for a long time it was supposed that the neutrino don't have a mass, so there were some terms missing, and recently they have been reinstated there. And Alain Kohn made this proposal before the discovery of the mass of the neutrino, but his proposal was flexible enough, so he did not have much difficulty to put it in. Okay. So what Alain Kohn said is that all these complicated things should be very similar to the electromagnetic case. But first for the Higgs boson, which gave him the hint. Instead of supposing that you have the universe is a four-dimensional manifold, suppose that there are two sheets, so two copies of the electron. And one is what? Due to the speed, there is a so-called left sector, left Carrier sector and right Carrier sector, and these two sheets should correspond to the two possible orientation of the electron and its particle. So, but what is the distance between these two? It's of the order of the Planck length, which is approximately 130 meters. Very, very small, of course. Far from being observable. So you imagine that the universe has two sheets which are very, very close to each other. And the boson has an attraction between the two sheets. Which means that the distance between the sheets is not strictly constant, it's a small variation. And this small variation are created by the Higgs boson. So it's a geometrical representation of the Higgs boson as Higgs boson as a distant, two-sheeted universe with a distance with the two. So this is the primitive idea. What Alain Kohn did was the following. M4 is a four-dimensional space-time of Minkowski, and there should be a finite non-commutative space. Don't ask me what it means. Really, it means, well, the idea which came from Gelfand is that if you have a compact space, it's a spectrum of the algebra of continuous function, and this so any commutative algebra defines a certain set of points, which is a space, and this was generalized by Grothendieck, and the name spectrum was chosen, well chosen, because Grothendieck started his career by studying the method of Gelfand in his thesis. So you can replace, if you have an algebra which is commutative and finite dimensional, it's just a model for a finite number of points. But if the algebra is not commutative, it's a more exotic object. But what Alarcon was able to do is to mimic all the construction of differential geometry. What is a differential form in this setup? What is the exterior differential, etc., etc., etc. And it was one of the motivations to build the so-called cyclic homology, which is very important in our object and rediscovered by many other people. Okay, so that's it. So what Alain says is that if you take this seriously, and if you do differential geometry on such an exotic space, not so exotic, okay, transverse dimension, it's more or less the same idea as the Kaluza line, but the fiber, instead of being one-dimensional, higher dimensional, 7-dimensional, or 8-dimensional, whatever, or 8-dimensional, 7-dimensional, is a finite set of points, but non-commutative. So, but it can express the very complicated formula for the action, for the Lagrangian and the action of the standard model in a very compact form. That's it. Now, what is a challenge? Challenge is the following: that in order to describe this model in complete form, you need to fix some parameters, some numerical parameters, which are really independent of any system of units. For instance, all these particles have masses. If you choose one of these masses as unit, they have ratio of masses, which are pure number, independent of any system. The electric charge, also properly normalized, is independent of any unit. Well, what is independent is alpha, which is E squared over 4 pi epsilon 0 a bar C in the standard units. So it's a pure number, which is approximately 1/37. At the moment, we have no explanation for this number. No explanation. There have been a lot of explanation. The best being that it's a license plate of the car of Dirac. It's too much. His license plate has this number. Okay. So, but we have no explanation. And of course, there are all kind of, when I say there are interactions, they are mediated, but there you have to fix certain constants. So you have approximately, well, I don't make an exact count, approximately numerical constant. Including, for instance, the mass of the Higgs, or all these masses have some estimate. No one has any explanation for these numbers. So you have a model. These numbers are obtained by statistical fit to experimental data. There have been so many experiments, there are very refined estimates of them. Most of them are defined, well, alpha is defined with 7 or 8 digits, even more, and also, well, so every time we do some experiment, we make more precise estimate of all these concepts. But so far we have no explanation for this concept. We don't know where they come from. That's a challenge. Okay, now, I will open the other side of the window, which is motifs and motivic. Motives, motivic homology, motivic periods, etc. This idea came from from Grothendieck, who stated it explicitly for the first time in the 60s, and almost immediately Manin published a paper on that, which gave some substance to that. And okay, Grothendieck, what was the motivation of Grothendieck? Well, motive has two meanings for Grothendieck. It's a motivation of geometry, and on the other hand, it's like in music, the motif, musical motif, the song which comes again and again. So what is a motive? Just take an example. Take the projective 3 space. Okay. Now, you count the number of points with coefficient in a finite field with Q elements. Well, a simple counting gives you 1 plus Q squared plus Q. A polynomial in Q. And it's the work of Henri Weil and then strengthened by Grothendieck and Deligne, shows that it's a very general phenomenon. When you count the number of points with coordinates in a finite field, it's usually a polynomial in group, not in all the group, but at least for a large class called the Tate varieties, it is true. Well, the origin of this is very simple to understand. Let's take P2, the projective plane. If you remove one line and to put at infinity, you have an affine plane, two independent coordinates. Now, two independent coordinates, each coordinate taking Q values for Q squared, so P2 Q squared. But now on the line, if you remove one point, which is on the line, you have a point at infinity plus a point at finite distance. They are, of course, labeled by Q possible coordinate, Q possible value for coordinate. So the line, so you have Q squared here, Q here, and 1 here, and that's make the comparison. So it's easy to describe, and there are many similar examples, and the people who know finite groups, Chevalier group, I mean, Chevalier was motivated by that kind of argument, and Tietz also. So, but the reason is that the space itself decomposes. It's not only that you count the number of points, it decomposes, as you have seen, let's say P2 of C can be taken as a union of C2, union C, C1, union C0. This is disjunct union, union. Okay, for the complex point, complex point over any field. So it corresponds to geometric decomposition, and this geometric decomposition enables you to calculate the cohomology group of the corresponding space. And here you see that the cohomology, there is something in dimension 0, something, well, C has dimension, topological dimension 2, so dimension 2, dimension 4. And if you compute the cohomology group of P2 of C, you will have something in dimension 0, something in dimension 2, something in dimension 4. So this polynomial encodes this decomposition and this cohomology. And of course, the great work of Weil first and then Grothendieck and Deligne was to give substance to that in very general. So that's now the remark by Grothendieck was that when you have a space like P2, let's say, it has cohomology group in dimension 0, cohomology dimension H2, cohomology in dimension 4. If you could split the space into pieces, but not we have to be careful. If you split it this way, all pieces will have only cohomology in dimension 0, no higher dimension numbers. So we have to be careful. So you cannot just say I decompose my space into pieces. A Tate variety, by the way, is a variety which has a similar decomposition, which explains why the number of points with Q is a polynomial. Okay, so you can imagine that there is a way to decompose, let's say, P2 into 3 pieces, each piece carrying one part of the cohomology. So what the piece cannot be an ordinary or manifold because the obvious example, even this one. So you have to invent a new object, which is obtained by taking a decomposition in direct sum of a variety into smaller variety. And the pieces cannot be ordinary varieties, so you call them motifs. And the point is that this motif, well, by means of a huge machinery of homological algebra, you can define rigorously what it means to take a factor, a direct factor of a P3, of a manifold like that, and to assign a cohomology to it. Not only a cohomology, but what Grothendieck discovered is that invented many different cohomology in algebraic geometry. Invented, well, ordinary cohomology is equal to the Betti cohomology. You take the complex point and you use standard homological geometry, let's say singular homology or cohomology. Then there is a Durham cohomology, building out of the differential form. And well, the great discovery of Grothendieck in '65 to extend the Durham to give a purely algebraic definition of the Durham cohomology, which gives a proof of another proof for algebraicity of the Durham theorem. Then Grothendieck invented the étal-elatic cohomology. Then he invented the crystalline cohomology, etc. So you have a lot of different cohomologies. But you expect that they carry more or less the same information. For instance, the dimension of a given cohomology group should be the same in all incarnations. And so the idea of Grothendieck was they should exist. They exist, we know already many cohomology theories. They are just the incarnation of a unique cohomology, which I call motivic cohomology. And he used the analogy of a beacon turning light and in the dark on the seaside, and then the light comes onto some village, then onto some boat, and onto some village, etc. So the light of the beacon is turning and illuminating from time to time a given site. And that was the image that Grothendieck had in mind. So he wanted to have a beacon, a cohomology theory, motivic cohomology, which would lie above all existing by suitable incarnation. Of course, incarnation means a certain factor from a certain category to another category. That's what it means. Okay, but then Grothendieck was interested into that, and so far, well, he proposed a certain program, which is formulated in the original paper. We have now exchange of letters between Grothendieck and Serre, which documents this, and there is a discussion in the 60s between Serre and Grothendieck. Grothendieck was very enthusiastic, Serre was more careful. Serre is always more careful at this step. Okay, and Grothendieck was a prophet. Read the letters from the exchange of letters between Grothendieck and Serre, you will see that. Grothendieck, the prophet, Serre. The miracle is this collaboration between so different people, who were bound by a strong friendship and enables a very good example. Okay, so that Grothendieck proposed a way to define them, but it failed. It failed because it rested on some very deep conjectures, which are close to the so-called Hodge conjecture, and most of the experts believe that they are not true in general. Well, Hodge conjecture should be true in many cases, but not in general. So the program failed, but it was resurrected in a different form by Wojewodsky and his collaborators some years ago, and now it's stable. And especially the special class of Tate varieties which lead to Tate's motif is well understood, well under control. Okay, now what does it have to do with the physics? What does it have to do with physics? Well, it has to do because the motif can provide you with numbers. Oh. Provide you with numbers. And these numbers, just to take a simple example, zeta of 2, zeta Riemann zeta function, by definition, is a sum of an